Welcome to the ProClimber podcast. In this episode, I talk to Manfred Kehrer. Manfred is a senior associate and building scientist at WJE & Associates in Illinois. For many years, he worked at the Fraunhofer Institute, along with Hartwig Künzel, developing WUFI. Manfred shares some insights into the early days at WUFI, as well as discussing the importance of hygrothermal modeling when designing buildings today. ProClimber inspires and educates people to create healthy, durable, and energy-efficient buildings to live, learn, work, and play in. Welcome to the ProClimber podcast, Manfred. How are things going for you in your summer over there, isn't it?
Thank you. It's pretty nice here, actually. Today not too warm, but we don't have the luxury you have. Nice warm weather all year round, right? I think.
Just to give our audience a bit of a background, Manfred, tell us about your life growing up in Bavaria, was it?
Yes, it is, actually. And I'm now curious who brought that thing to you. Well, probably one of you German guys. What's his name? Thomas van Ramstonk, isn't his name? He probably feeded you with that question. Isn't that the case? Actually, Bavaria is pretty funny and nice. I mean, southern part of Germany, mountains, nice lakes. Vacation area for northern Germans and other people from Europe and all over the world. Skiing wintertime is pretty cool. Good beer, lederhosen, slap dancing when I was young. I did all that. So, yeah, can't complain. It's a nice area. However, I like New Zealand too. I've been there a couple of times, so that's pretty nice as well. And actually, what Thomas feeded you that question, you should know that I think he has a Bavarian citizenship, kind of fake thing. Ooh. He got from some guys he studied with in Rosenheim. I think he said that to me. So, yeah, it's kind of funny.
And tell me, Manfred, I believe you enjoy brewing beer on the side. Is that right?
I did that, yes. As a Bavarian, what do you expect? And that was actually pretty... I stopped that. It's a lot of labor work and my back isn't good anymore. So the lifting stuff is, not as it was in earlier times. So I stopped that probably about 13 years ago.
I believe you've got some special water that you use for the beer brewing.
Did I? I'm not sure what you're alluding to. I think I used one time the wrong water, which was, I think it was in Tennessee, and the anti-badge I had to throw away, so that wasn't very nice. But I also was seeing with your ProClimber guys in Wellington, a brewer there, I think what's the name of that? And they had the most hoppiest beer, at least on earth. At least they claimed that. So I'm not sure it was true, and it wasn't tasty good because I don't like IPAs.
Yeah, IPAs have become super sort of popular all of a sudden, haven't they?
Yeah, all over the place. The US, the same thing. Not my cup of tea, actually.
So growing up, what prompted you to get into building physics?
It was luck, pure luck. I never wanted to be in any construction stuff. I studied building science. I studied physics. Stupid. Physics at the University of Applied Science in Munich because I just love physics and cosmology and all that. And then it was just luck. On some point you need to find a place for internship, and Holzkirchen by Fraunhofer IBP is probably about 30 kilometers south of Munich, maybe 50. And that's very close where I was born and raised. So they have this Fraunhofer Institute for Building Physics. And I needed something to do a physics internship. So, okay, physics in the name, not bad. Let's go there. It's close to it. And that was the way I came to the Fraunhofer Institute. It was back in 1988, I think. Yes, 88. And, then I stuck with building science the rest of my life. So I can't complain. It's pretty good, but I never thought this would be my career.
And how did you meet up with Hartwig?
Hartwig Künzel, I guess, right?
That's the one.
Yeah, well, there was certainly at the internship. I didn't work for him at that time. He had a colleague called Ulrich Möller, I think. Yeah, it was his name. And he was more working on moisture and structural stuff of cladding systems. And did a lot of ANSYS work at that time, so structural analysis for when stuff get wet. And he was just office next to Hartwig. And I picked up some stuff from Hartwig as well, some work for him, some WUFI 2D calculations actually back in 1988. I did to compare this with ANSYS calculations, which we kind of abused to make moisture calculations. I forgot what the results was. So that's where I first time met Hartwig. And then over the years, it was more that I worked stuff for him and with him. And and that was 1988. What is that? 30 years ago? 32 years ago, right? Long time. Damn, I'm old.
So how was it back in the early days of WUFI that with you guys working together? How did the whole concept come up and developing the software and things?
Well, the entire WUFI software actually was developed during funding of heritage protection program from the German government. So at that time we had the acid rain stuff and all these old churches with the nice sandstones. They had the exterior surface turn into black stuff from the air, from the smog. And it was very clear that moisture transport is crucial to understand what's happening, to find a solution how to get them clean again. And under that funding, the WUFI was actually developed during the 80s. And Hartwig, who is the grandfather of WUFI, probably we can say that, did all that work and actually was really able to simplify the complex physics of heat and moisture and put it into a software with relatively simple input parameters so that you can nowadays even use that for construction practice on many other applications. So that step has been done, I think, in the 90s. When the funding was kind of over or canceled, governmental funding, you never know what's going to happen next year, right? So then I think Hartwig was, and I wasn't involved, I think probably in about maybe end of the 90s, I was starting to get involved in the development. And that's how it worked out to come from brick masonry and cladding stuff and sandstones to the building materials we have today in residential and commercial construction.
So what was around before WUFI was developed? Was it the Glaser method you were using?
Yeah, it was the Glaser method using, and there's still people doing this all over the world, and still they do this actually in the US. So many times I get asked to do a dew point analysis, and then I have a hard time to explain, okay, that's ancient history, and explain them that this is I don't want to say a wrong way to look at things, but an archaic way nowadays to look at things.
So when you talk about WUFI and the differences between the Glaser method, can you explain how WUFI actually works for us?
Let's actually go back what the Glaser method actually does. So the Glaser method gives you an idea where you might have a condensation point somewhere in your assembly, but only on a steady state. That means not time-changing boundary conditions. So you have one cold temperature on the outside, you have here 20 degrees Celsius on the inside, and then with some moisture values like perm values, well, you probably use the MVTR, I think, in New Zealand. What is that?
Yes, that's the
moisture vapor transmission resistance. Is that correct?
Resistance, yeah.
Okay. But that has a lot of problems because the Glaser method doesn't take into account that things are changing over time. You have a rain event on the outside. You have your sun hitting the surface, warming that up. Now, some heat flows to the inside, some heat goes from the surface then to the outside air. Then you have liquid transport, you have vapor transmission. Okay, vapor transmission is actually taken care of in the Glaser method pretty good. You have storage, of course, moisture storage, which is not necessarily a bad thing. Brick gets wet, nothing wrong with that, unless we talk about freeze and thaw damage. But otherwise, let me just put that off here. And WUFI actually is able to deal with a lot of those things. So we take the sun into account, rain events, liquid transport through your system, depending if you have liquid transport. So brick or CMU is probably a good example for that. And so we have better results. Not saying that the Glaser method is wrong, it's just very conservative. And we know from practice, actually, if you apply the Glaser method, it would actually say that a lot of systems fail, which we built for decades without an issue. So it's a little too conservative on that part.
So just to understand, once you developed the software, how did you actually validate that the results were going to work in real life?
Well, we had the big luck, actually, that Holzkirchen, where Fraunhofer is located south of Munich, is actually originally a field test site. And that goes back to the 1950s. So it was actually it's a very rural area. And in the 1950s, from the people living there, you got to see their point. There come these science guys, they buy a bunch of land and build houses on there, test houses, where no one lives in there. So their nickname was Ghost Town, of course. That's what was it since the 1950s. And I know a lot of bunch early in the 80s, they even know that term very, 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 very good. So the good thing with validation is that the field test sites since the 1950s, we have all the buildings there, and instrumentation and the instrumentation expertise to actually do measurements on these buildings and then apply with simulation and with simulation results. And there has been done many, many things, and it probably goes too far to go in details. But at some point in the 90s, we were very confident that it can be very helpful, the simulation results. We also figure, and at some point, that's pretty interesting. You always think, at least back in the 80s and 90s, maybe today not that much no more, but at that time, when measurement and simulation didn't work out in building science, everybody said, oh, your code is wrong. And what people don't know is how many times we discovered measurement errors because we figured out that, I mean, at some point we've seen that the measurement and the simulation doesn't work out well. But on some point we knew, okay, we cannot be that far off as a simulation. We don't know we are totally precise, but we can't be that far off. And then if you dig a little more into the measurements, calibration factors off by factor 2. So we had that. It existed. And then later on in the 2000s, more models came into software, nighttime overcooling. This is something I programmed and designed. Sources and sinks, cladding ventilation, that's something I did as well. And we had optimal options to validate all these calculation results.
So what are sort of the most common moisture problems that you're finding in buildings, and how can WUFI help in mitigating those issues?
Rain leakage is probably the most important problem, and that probably wouldn't surprise you in New Zealand because you were one of these victims. I think it's probably called there, is it called in New Zealand leaky house syndrome or something like that?
Leaky building syndrome, that's the one.
And the same happened in Sweden in the 1990s, and the same happened in Canada, British Columbia as well. I think the same time in the 90s mainly. I'm not sure how it was in New Zealand where it started. 80s, 90s, 2000s maybe too.
Yeah, late 90s, early 2000s, yeah.
Pretty much exactly where it happened in Sweden and in British Columbia, I think, as well. It's just rain comes in and cannot get out. And there was huge damage, billions of dollars and thousands of buildings. I mean, probably in British Columbia only was many thousand, and certainly 1,000 plus in Sweden, and I don't know the numbers for New Zealand. And that came all because someone transferred a building product or a cladding system. I think it's mainly the case in New Zealand. It's also in Sweden. The cladding system just transferred from a different climate zone with different building, applied to different buildings, to another climate zone where the construction underneath is different, without even knowing what they're doing. And then down the road, we have all these issues. So that's probably what is common with all these experiences from Sweden, New Zealand, and British Columbia.
We're actually now facing the next level, which is what we're talking a lot about, which is the internal moisture, because we've got a big thing where New Zealand is increasing the insulation values at the moment, but no requirement for airtightness, vapor control, or ventilation. We're relying on opening windows.
Yes, we know that. I think Germans had that too. And when you increase the air tightness, then the moisture doesn't leave the building as good, right? That's not a problem in the US because we have HVAC systems and they have outdoor air, so there is some ventilation going on normally. But it's a problem in climate zones where you don't have air pumping around and taking care of that. How do you solve that, actually? Let me ask you that.
Well, we're talking to them about, the requirement for some form of mechanical ventilation, continuously replacing the air within the building, and ideally with some sort of a heat recovery if possible. I've just installed one of those in my own house, and it's been a real eye-opener to see how it actually works. Reducing moisture, CO2, and the level of heat recovery is just fantastic at virtually such a low energy usage. I think mine's using 45 watts of electricity. So pretty crazy the sort of efficiencies these devices offer.
Yes, it can be, but then you're right. The moisture is an issue because humans create moisture, cooking, showering, just through the skin. And then you have animals, pets, plants, aquarium, a lot of stuff can produce moisture, right, in a building.
Exactly. And then we were obviously talking to them about air tightness and vapor control layers too, because currently we're relying on our linings to control the airflow in and out of the building.
Yes, the intentional airflows, right? I mean, the outdoor air, mechanical air inlet is something by design, but the unintentional airflow is something we don't like, but it exists all the time. That's a big difference compared to other things we build. I always compare it to a car. So you don't buy a car, open the lid, get a drill in the engine, and then expect the car still works the same way it did before, right? You don't expect that. But we expect this with buildings, and we do that all the time. We change a lot of things. We make holes in the wall. We change this and this and that. And then at some point we make mistakes, and then something happens. Yeah, a rain intrusion or something like that. And yeah, and the airflow, of course. Yeah, which transports moisture, and the moisture then, when you're on the colder side, produces issues. That's what it is.
So one of the challenges with building science is obviously that long-term predicting of performance. How does WUFI modeling help with the durability of the long-term performance of a building?
That's a little tough, actually, because now we talk a lot of things we don't know of. We know the material properties, which we can measure for a lot of things. We don't know the specific air tightness and the airflow paths. We don't want to have them, but they exist. We don't know the rain leakage behavior. There is a little, roofs cannot have any rain leakage. Wall system, we know there is a little rain intrusion, and some of that is okay if the system is, and some actually are designed to have that through your cladding. But some of that, even if you don't precisely design for that, is acceptable depending on many other things of your assembly and the climate zone and the way you live in there. And all these unknowns you have, that makes it hard to make a really precise long-term prediction. So you need to know what you do, and normally it comes along with some sensitivity analysis. I mean, if the performance of your WUFI calculation depends only on the unknown parameters, well, then it's actually not useful to use the results because you don't have a conclusion, right? Unless you go a little back and say, okay, it works only if this value stays below that and this value below that. That is possible. But typically you want to have your system being as much independent from the unknowns, which is sometimes out of your control, of course.
We're finding that with the climate in New Zealand at the moment, we're getting a lot of these sort of 100-year rainfalls and things occurring. What is your advice for that sort of thing?
So you talk about climate change, I guess, because if you have every year the 100-year rainfall, then the ancient 100-year rainfall is not the current 100-year rainfall no more, right? That's if you would have the data on how the climate changes, you certainly can create WUFI climate. Well, I probably want to back up a little. What WUFI typically does is you click from one location. I think you have a dozen of these in New Zealand. They should cover the typical behavior of New Zealand, actually. I think they do. Then there is one typical year of weather in the database behind that. And it runs it all the time. If you make 100-year-long calculations, it runs 100 times this 1 year of data. So climate change is actually not really taken care of. You could, of course, create your own climate file with the data. The question is, where do you get the data from? And then you probably have a big variety of the next uncertainty. What is that? You can maybe even AI generate the climate change. But on the other hand, I would feel not very good if I consult my client who pays me to give him something which is actually depending on the AI I put in. I wouldn't like that, actually. That change is probably, it's tough. I won't say it's tough. Actually, that goes back to do a conservative design and don't design on the edge. Because if one of these unknowns goes a little this way and you fall off the cliffs, that's something you cannot really recommend to your clients.
And is WUFI ideal for both new construction as well as renovation or retrofit projects?
Sure. There's no reason why you want to limit it to only one. There's an ASHRAE standard 160 in the US that talks about design criteria for, what is it name? Actually, a standard which explains how to use a tool like WUFI to design your wall system properly, depending on climate zone and stuff. And that one is for new construction, obviously, and for retrofit or for failure investigation. It is a good tool as well because it's based on the physics and the thermodynamics and everything we know from moisture transport and thermodynamics, how physics work in that area. And is just programmed in a nice software. So that can be very helpful.
So what are some of the most surprising sort of insights or results that you've encountered when you've been running WUFI models?
I just recently had a publication actually for composite roof decks in the US. I'm not sure if this is common in New Zealand. So you have wood truss roofs, and they're probably 30, 40 inches. What is that? Maybe a meter tall, totally filled with insulation. Typically from the outside, just blown in insulation, because if you don't fill it totally, you have to have sprinkler systems because of the fire code. That puts in a cold climate zone, the sheeting on the outside on a very cold temperature. And then, of course, what do you do with the duct systems of your HVAC system? Well, you put it just in this perfectly placed there because it's nicely hidden. And the ducts are leaky, and they pump a lot of indoor air onto the sheeting, which is typically in a cold climate zone below the dew point of the indoor air, and you deliver a lot of moisture to that roof deck. So that was just about 2 years ago. I wasn't really very successful to kind of model the duct system and the leakage to produce that damage. We did something else to show what the damage could look like. So that was a little surprising that I wasn't that good in that application.
Now, when it comes to training up on WUFI, obviously we've got Jesse that's running trainings for us out of Australia. Obviously, there's a lot of different inputs that you need to make. And one of the challenges we have here in New Zealand is that a lot of the products are not currently available as products within WUFI. So how do you go about actually inputting product and working with products that are not available on the system?
Well, that goes back to, you got to know what you're doing. So that means you need to understand the building science basics. Because, as you just mentioned, you don't have all the properties. And even in the US, you don't have all the properties. Typically, you get a perm value or your MVTR values. That's pretty good. But there is a lot of other stuff. Moisture storage function, you don't get this. So typically, you take a material which is similar than that you have, and then adapt this with the properties you have from the product. Now, that can be very simple. It can be very complex. For a membrane, it's very simple because when we have membranes, the only thing matters is the MVTR value. Thermal conductivity, thermal storage, moisture storage, everything of that is irrelevant. It's just that number. And you typically have that. So you go to the database, you get some membrane, you put your other perm value or MVTR value in there, and you're good to go. For bricks, that's a little different story. Bricks vary a lot. In liquid uptake, in bulk density, how much water they can absorb, what freeze thaw damage they may suffer or not. Then it gets complex. So going back to the conservative approach, you use a very thirsty brick, likes a lot of water. The WUFI database has that. That's what I normally use. And then see how your system behaves and whether the system actually shows some issues or not. If it shows some issues, well, then you got to have better data for your brick. Very often that's the case, not only, but very often. And then story goes on, and many ways are then possible to, at the end, satisfy the concerns or the questions of your client.
So talking about the client, what sort of outputs can they expect from the WUFI report?
You got to figure out whether the person who did the WUFI analysis is capable to do the job. And I have to say, very often I review stuff where I have my doubts on that. And so a very good thing is whether, if you look at the report, if someone just says, well, all the input data are in that automatic WUFI report, which WUFI creates, and doesn't talk about that, that normally makes me suspicious. Because the WUFI report is a little academic and some important stuff is not in there. So it has pages of all these curves and properties for the materials, and most of them are not necessarily important. So someone who runs the WUFI analysis should certainly address the important input data for that simulation, which change depending on a lot of things, and what the numbers are and why are they have chosen that way. That is something. If I don't see this in a report I review, I'm certainly a little concerned and ask a little further. So what it should have? Well, This ASHRAE standard 160 in the US says now for a bunch of years, I think since 2016, you should do a mold growth evaluation. We typically know it's not 100% sure, and there's still some science going on whether what I'm saying right now is correct, but typically mold growth is the first problem you experience. If you can limit mold growth to zero or non-visible or below, let's say, mold spore germination, that's a term for that, then you should be probably fine with all the other moisture issues, probably. So therefore, it's in the ASHRAE standard 160 to do this mold growth index evaluation. There is a very complex math to do that, but WUFI does that for you. We have a post-processing module. You just click on a specific position. You enter something like the sensitivity of the substrate for mold growth. Obviously, a paper-faced gypsum board is more prone or more vulnerable to get a mold growth than maybe a brick surface. So the model does that take into account. And this is normally what I want to see. And then beside that, we have some values, and they are not in the standard yet. What is critical for moisture content for wooden-based material? So typically, I always use 20% by weight. That's a critical point. If you can still for wood-based materials, if you can stay below that threshold, you are fine with mold growth, fine with wood decay. If you're above that, let's get back. And most of the cases, you can design your system to stay below that 20%. Water content by weight, that's the number behind. And then we know if you are above 27, 28%, up to 30%, then you certainly will have, if it occurs for a longer time, then you certainly will have wood decay. So that's a metric I typically use. We have something for gypsum boards as well. 2% per weight is a typical threshold for the maximum content. And that has turned out to be very, very helpful. So this is normally what I look for, the MGI, mold growth evaluation, and then maximum water contents for wood-based materials and gypsum boards.
One of the challenges that we have in New Zealand is that because currently we don't have a specific requirement for air tightness, it gives us a challenge sometimes with running WUFI models because we don't have a defined air tightness level. Is there anything you can do to assist with calculating where you don't have a specific defined air tightness?
Well, you have to assume one. That's simple. So there is a model in WUFI there which calculates for cold climate zones what amount of moisture you would expect on the exterior sheathing from in the interior higher absolute moisture, depending on the airflow, which depends on the airflow depends on your building air tightness and the pressure difference from in to out, which we typically calculate just by stack effect. So if you know the building height and the temperature inside and outside, and the temperature is part of the WUFI climate file, that's pretty simple. So if you neglect some mechanical overpressure, which I think you can do in most New Zealand houses, I presume, then you have a rough idea what moisture consequence your air tightness has over the winter season. What air tightness to use? Well, I use the IACC regulated maximum air leakage of 0.4 CFM per square feet at 75 pascals. That's probably a good number for the US. I'm not sure about New Zealand, actually.
So currently for sort of residential buildings, we're seeing a number of about 5 air changes per hour on a blower door test.
Okay, that seems a lot. Now we need to have the building height to transfer that to cubic meter per hour and per square meter of wall surface or closure surface. I think that's it. You certainly can do that. So if you get that number in there and your building height, which is probably 2 stories or 3 stories for residential homes typically, you have an idea how that works. And there have been done studies in Germany that validate that approach. It's, of course, a little more complex because air flow is a 3-dimensional phenomenon. And we try to smear this all over the one board in a 1-dimensional calculation. However, it's certainly better to use that instead of using nothing, because that gives some load on your system. And then you can compare, is that system better versus that system for typically when we have clients, they ask us, okay, should we have the air barrier on the outside low perm or high perm, or low MVTR value, high MVTR value? And this is a very good option where we can actually just compare and you figure out what is the better and drier option.
So, Manfred, we're starting to get a lot more people wanting to start using WUFI in New Zealand, which is great. When they go along to the website, how do they choose which version to pick?
Always the most updated, but I think that wasn't your question. Your question was about the 3 WUFI versions we have around, actually 4. Okay. So there's a WUFI Pro and a 2D and a Passive and a Plus. Is that what you're referring to?
That's right. Yeah.
Well, WUFI Pro is what I mainly talked, actually, because this is what I typically do. Just to get a good wall design, depending on the climate zone you live. It's just a one-dimensional wall system, no windows, no doors, no edges, no wall-to-roof connections and all that. And that's pretty helpful for this. So you don't have no corners, no thermal bridges, nothing like that. Now, as of course we have joints to windows and doors, thermal bridging, then you have a WUFI 2D that can do that pretty good, I want to say. With the one problem, it's not as user-friendly as the 1D. So normally I suggest if you are not an experienced WUFI 1D or WUFI Pro user, or have experience in another multidimensional transient software. So transient means over boundary condition changing over time, and then of course the airflow and the moisture transport changes over time every single hour. That's what WUFI typically calculates. If you don't have either of that, then you shouldn't use WUFI 2D. That's at least my recommendation. WUFI Plus is then more building an entire house out of walls and roofs and basement, and is more for energy consumption prediction. And the WUFI Passive house is, as far as I know, I'm not such an expert in that, a smaller version of the WUFI Plus.
So looking forward, what do you see as ongoing research and developments of WUFI in the future?
We still have the airflow problem is not totally solved, and maybe we never solved that properly. There's certainly some need to get this a little better, I think. If we ever get there, I don't know. It could be. I don't want to say no, but I don't see the path now. So there's certainly something we should do. More material data, more material properties into the database, certainly an option. More brand names. I'm not sure what the New Zealand database looks like. The American gets a little bigger with brand names, and we do the measurement here in our wonderful lab, I want to say at WJE in Northbrook, Illinois. So typically clients come to us, measure the stuff, and it gets into the database. That's what we do, something like maybe once, twice a year, so that the user has more options to choose from when he's building his assembly. And that's pretty much it. I don't think anything else as of right now, but I may have forgotten something.
Now, Manfred, we're coming to the end of our discussion here this morning. I've got a question from Jesse. He wants to know, since you've moved to the US, which flag are you flying at the top? Is it the Bavarian flag or the US flag?
That's from Jesse?
From Jesse.
I think I met him once, and I think it was in New Zealand on one of the workshops I did there. Yeah. That means he knows that I had both flags in my ex-house in Tennessee. I mean, I moved. It must be, I think, because I had both their Bavarian flag and the US flag. And they were exactly the same height, which is actually not what you're supposed to be in the US. And I don't think I will do this again. I mean, I've been told this afterwards. I've did that many years ago. And as I'm now a US citizen, I probably should use the US flag a little higher always. And I probably will do that.
Thank you so much for your time this morning, Manfred. It's been excellent catching up. Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.